The night sky, when viewed from a dark and quiet place, feels eternal. When we stand beneath that vast canopy of stars, breathing in the cool air of a midnight watch, it is easy to believe that the cosmos has always been this way. The constellations seem fixed and immutable, diamond dust scattered across a canvas of velvet obsidian. For thousands of years, human beings looked up and assumed that the universe was static, a stage that was built once and had remained unchanged ever since, waiting for the drama of life to unfold. It feels permanent, it feels stable, it feels timeless. Yet we now know that this stillness is an illusion. The universe is not a painting, it is a river. It is flowing, changing, and evolving. Every galaxy we see is drifting, carried along by the currents of expanding space. If we possess the patience to watch for billions of years, we would see the stars burn out one by one, the great nebulas disperse, and the galaxies retreat into the shadows. We live in a dynamic, restless cosmos, and because it is changing, it demands an explanation. If it is expanding now, it must have been smaller yesterday. If it is cooling now, it must have been hotter in the past. This line of reasoning leads us backward, rewinding the great cosmic film until we arrive at the dominant narrative of our time, the Big Bang. It is the story we have told ourselves for the better part of a century. We are told that 14 billion years ago, everything we know, every star, every planet, every atom in your body, and even the fabric of space and time itself, erupted from a single point of infinite density and temperature. In a fraction of a second, the universe went from the size of a subatomic particle to the size of a galaxy, stretching outward in a violent, majestic inflation that set the clock of eternity ticking. It is a compelling story. It fits the data we gather from our telescopes. It explains why the distant galaxies are rushing away from us. It explains the faint, ancient heat that still glows in the background of the sky, the afterglow of that primordial fire. It feels complete. But there is a silence at the heart of this theory. There is a shadow where the light of understanding cannot reach. When physicists take the equations of general relativity, the rules that govern gravity and the shape of space, and apply them to that very first moment, something troubling happens. The mathematics breaks down. The equations stop making sense. We trace the history of the universe back through the formation of the first stars, back through the cooling of the first atoms, back to the first few minutes when the cosmos was a fusion reactor. But when we try to push back to the absolute beginning, to time zero, we are confronted with a singularity. A singularity is a place where the laws of physics simply give up. It is a point of zero volume and infinite density. It is a mathematical impossibility, a divide by zero error in the code of reality. It suggests that the universe began as a point with no dimensions, containing all the mass and energy that would ever exist. For many scientists, this is not an answer. It is an admission of defeat. It is a sign that our theory is missing something fundamental. To say that the universe sprang from nothing or from a point of infinite density requires a leap of faith that sits uncomfortably with the scientific mind. So, we are left with a profound question, one that keeps cosmologists awake in the quiet hours of the night. What if the Big Bang was not the beginning? What if the universe has a history that stretches back before that first violent expansion? What if the singularity is just a veil, hiding a deeper, more ancient reality? Tonight, we embark on a journey into the unknown. We will drift past the edge of accepted history and explore the alternatives. We will ask what might have existed before the beginning. We will consider the possibility that our universe is just one breath in an infinite cycle, or a bubble in a much larger sea, or perhaps the interior of a black hole in another dimension. We will explore the idea that time did not start 14 billion years ago, but that it has been flowing forever, winding through eons and eras that we are only just beginning to imagine. To understand why we need these alternatives, we must first appreciate the magnitude of the problem with the Standard Model. Imagine, if you will, the universe as it was just after the beginning. We are not talking about the first year or even the first day. We are talking about the first trillionth of a second. This is known as the Planck era. In this unimaginably brief window, the universe was so hot and so energetic that the four fundamental forces of nature were fused into one. Gravity, electromagnetism, and the nuclear forces were indistinguishable. We have no experiments that can recreate these conditions. Our most powerful particle accelerators, which smash atoms together at near the speed of light to uncover the secrets of matter, cannot reach energies anywhere near those of the Planck era. We are blind to this moment. And yet, the Big Bang Theory asks us to accept that before this moment, there was a singularity. It asks us to accept that time itself began here. This concept of a beginning of time is difficult to grasp. St. Augustine, the philosopher and theologian, once asked what God was doing before he created the world. His answer was that there was no before, because time was created along with the world. Modern cosmology echoes this sentiment. Stephen Hawking famously compared asking what happened before the Big Bang to asking what is north of the North Pole. There is nothing north of the North Pole. The question loses its meaning. The geometry of the Earth closes off the possibility. In the same way, the geometry of four-dimensional space-time is thought to close off the past at the Big Bang. But this answer feels incomplete to the human intuition. We are creatures of cause and effect. If the universe expanded, something must have caused it to expand. If the vacuum was filled with energy, where did that energy come from? The idea of a genesis from absolute nothingness, no space, no time, no matter, no physics, feels like a magic trick. Furthermore, the Big Bang Theory, for all its successes, leaves us with some strange coincidences. When we look at the universe today, we see that it is incredibly uniform. The temperature of the deep cosmos is almost exactly the same in every direction we look. If you look at the microwave background radiation on one side of the sky, and then turn 180 degrees and look at the other side, the temperature matches to within a tiny fraction of a degree. This is puzzling because, in the standard Big Bang model, those two opposite sides of the sky have never been in contact with each other. They are too far apart. Light has not had enough time to travel from one side to the other since the beginning of time to equalize their temperatures. It is like placing a cup of coffee on a table in Paris and a cup of coffee on a table in Tokyo, and finding that they are exactly the same temperature down to the millionth of a degree without ever having been in the same room. To fix this, scientists invented inflation, a period of extremely rapid expansion that happened right after the birth of the cosmos. This theory suggests that the universe started as a tiny speck, allowing it to equalize its temperature, and then suddenly blew up to a massive size faster than the speed of light. Inflation works. It solves the mathematical problems, but we still do not know what caused inflation or why it stopped. It is a patch, a brilliant, effective patch applied to a theory that creates as many mysteries as it solves. This is where the doubt begins to creep in. This is where the silence before the singularity begins to whisper. Perhaps we are trying too hard to force a beginning where there was none. Perhaps the universe did not arise from nothing. Perhaps it arose from something else. Imagine for a moment that the breakdown of physics at the singularity is not an end, but a bridge. What if, when we run the clock backward, we do not hit a wall, but rather pass through a transition? What if the bang was actually a bounce? There are models of the universe, grounded in rigorous mathematics, that suggest our cosmos is the result of a collapse of a previous universe. In this view, a universe much like ours existed before this one. It had stars and galaxies and perhaps life. Over billions of years it expanded, but eventually gravity or some other force caused it to contract. It shrank smaller and smaller, growing hotter and denser until it reached a critical point. But instead of crushing down into a singularity of zero size, quantum effects intervened. Just as an atom prevents electrons from crashing into the nucleus, perhaps the fabric of space-time resists being crushed to nothing. The contraction halted, the energy built up like a compressed spring, and then, snap! The universe rebounded. The contraction became an expansion. The death of the old universe became the Big Bang of the new one. If this is true, then the first moment was not a beginning at all. It was merely a turn of the seasons. It was the start of a new cycle in an eternal rhythm. The silence before the singularity was not the silence of non-existence, but the silence of a held breath before a great exhalation. Consider the implications of this. It would mean that time has no beginning. The timeline stretches back forever, an infinite chain of universes rising and falling, born from the ashes of their predecessors. It removes the uncomfortable question of creation and replaces it with the grandeur of eternity. But the bouncing universe is just one of the whispers in the dark. There are stranger ideas floating in the deep waters of theoretical physics. Some physicists suggest that our universe is a three-dimensional membrane, or brain, floating in a higher dimensional space called the bulk. Imagine sheets of paper floating in the wind. Occasionally, these sheets might drift close to one another. If two of these higher dimensional membranes were to collide, the energy of that impact could look, to the inhabitants of the membrane, exactly like a Big Bang. In this scenario, the singularity is not a point of infinite density, but the moment of impact. The history of our universe began at the collision, but the history of the bulk, the greater space in which we float, is much older. It suggests that there are other universes, other brains drifting nearby, perhaps only millimeters away from us, in a fourth or fifth dimension that we cannot perceive. And then there is the view that looks not at dimensions but at the nature of matter itself. When a massive star dies, it collapses under its own weight to form a black hole. Inside a black hole, matter is crushed to a point of infinite density, a singularity. This sounds suspiciously like the description of the Big Bang. This similarity has led some bold thinkers to propose that our universe is actually the interior of a black hole. In this mind-bending hypothesis, what we perceive as the Big Bang was the formation of the black hole in a parent universe. The event horizon of the black hole, the point of no return, acts as the boundary of our cosmos. As the black hole in the parent universe consumes matter, our universe expands. We are living, quite literally, inside a star that has collapsed in another reality. And perhaps the black holes in our own universe are the seeds of new baby universes, creating a fractal cascade of realities, universes within universes, stretching down infinitely. These theories, the bounce, the brain collision, the black hole cosmology, are not mere science fiction. They are serious attempts to solve the problems that the standard Big Bang theory cannot. They are attempts to look past the singularity, to peer through the fog of the first moment and see what lies on the other side. As we lie here in the dark, contemplating these immense scales, we must let go of our human attachment to beginnings and endings. Nature, as we observe it on Earth, is full of cycles. The sun rises and sets. The tides flow in and out. The seasons turn. Plants grow, die, and decompose to feed new life. Why should the universe be any different? Why should the cosmos be a straight line with a start and a stop, when everything contained within it moves in a circle? The silence before the singularity is not an empty void. It is a heavy silence, pregnant with possibility. It is the silence of a library before the doors open, or the silence of a forest before the dawn chorus. It is a space waiting to be filled with knowledge. In the chapters that follow, we will walk through these alternative histories. We will listen to the voices of the scientists who dared to challenge the orthodoxy of the Big Bang. We will explore the calm, steady vision of a universe that never changes. We will visualize the titanic, slow-motion collisions of higher dimensions. We will imagine the view from inside a black hole. And we will consider the geometry of a universe that forgets its own past to be born again. We are travelers standing at the edge of a cliff, looking down into a mist that hides the valley below. The Big Bang Theory tells us that the cliff is the edge of the world, and there is nothing beneath the mist. But the alternative theories invite us to believe that if we could only see through the fog, we would see a landscape more vast and ancient than we ever dreamed. The night sky is not just a ceiling, it is a window. And as we gaze through it, we realize that the light hitting our eyes is not just telling us where we are. It is asking us when we are. Are we at the beginning of time? Or are we simply passengers on a voyage that has no beginning and no end? Let us drift now away from the hard certainty of the single point and float into the open waters of the unknown. Let us turn the page on the standard story and open the book of the impossible. The singularity is not the end of the inquiry. It is the starting line, and the silence is about to be broken. There was a time not so long ago when the origin of the universe was not a settled matter of textbooks and television documentaries, but a fierce battleground of philosophy. In the middle of the 20th century, before satellites mapped the afterglow of creation, and before computer simulations traced the webs of dark matter, the scientific community was divided. On one side stood the proponents of a violent, explosive beginning, the theory that would eventually be christened the Big Bang. On the other side stood a group of thinkers who found the idea of a sudden, inexplicable moment of creation to be scientifically ugly and philosophically unsatisfying. They proposed a different kind of cosmos. They dreamed of a universe that was calm, eternal, and unchanging. They called it the steady state. To understand the allure of this idea, we must step back into the mindset of the 1940s. The world had just emerged from the chaos of a global war. There was a hunger for stability, for things that lasted. When astronomers looked up at the night sky, they saw the same constellations that the ancient Egyptians and the Babylonians had seen. The stars appeared fixed and reliable. While it was true that Edwin Hubble had discovered that the galaxies were drifting apart, implying that the universe was expanding, it did not necessarily mean that the universe had a birthday. For three brilliant physicists, Fred Hoyle, Thomas Gold, and Hermann Bondi, the idea that the universe sprang from a primeval atom yesterday, metaphorically speaking, felt like a cheat. It felt like the physicists were giving up. If the universe had a beginning, then science had a hard limit. You could ask what happened 1 minute after the beginning, but you were forbidden from asking what happened 1 minute before. To a mind like Fred Hoyle's, which was fiercely rational and deeply skeptical of anything that smelled of religion or mysticism, a moment of creation sounded far too much like a supernatural event dressed up in mathematics. So, one night in 1948, after watching a horror movie about a ghost story that looped in a circle with no beginning and no end, the trio began to formulate an alternative. They asked a simple, elegant question. What if the universe has always been here? What if it has no beginning and no end? What if, when you look at the cosmos 1 billion years in the past, or 1 billion years in the future, it looks essentially the same as it does tonight? This was the core of the steady-state theory. It was a vision of profound serenity. In this model, the universe is not a film with a start and a finish. It is a painting that is constantly being touched up. It stretches infinitely into the past and infinitely into the future. There was no chaotic explosion. There was no singularity where the laws of physics broke down. There was only the eternal now. But there was a problem, a massive hurdle that any student of physics could point out. We know the universe is expanding. The galaxies are moving away from one another. If you have a room full of people and the walls move outward, the crowd gets thinner. Over time, the room becomes empty. If the universe has been expanding forever, why is it not a vast, dark, empty void with no stars left? Why do we still see galaxies clustered together? If the universe is eternal and expanding, all the matter should have thinned out to nothingness trillions of years ago. The solution that Hoyle, Gold, and Bondi proposed was audacious. It was a concept known as continuous creation. They suggested that as the galaxies move apart and the space between them stretches, new matter simply appears to fill the gaps. This creates a beautiful, almost magical image in the mind. Imagine the vast, dark deserts of intergalactic space. As the fabric of the cosmos stretches, pulling the galaxies away from each other, the universe gently hums with a low-level creative energy. Out of the vacuum, seemingly out of nowhere, a single atom of hydrogen pops into existence. It is not a violent event. It is a quiet addition. One atom here, another atom there, 1 million light-years away. This new matter, born from the energy of the expansion itself, would slowly clump together under the force of gravity. Over billions of years, these clouds of hydrogen would collapse to form new stars and eventually new galaxies. So, as the old galaxies drift off into the unobservable distance, passing beyond the horizon of our vision, new galaxies are born to take their place. The density of the universe remains constant. The stage remains full of actors, even though the individual actors eventually exit the stage. To the critics who cried that creating matter out of nothing violated the laws of physics, specifically the conservation of energy, Hoyle had a witty and sharp rebuttal. He pointed out that the Big Bang Theory required all the matter in the entire universe to be created out of nothing in a single instant. The steady-state theory, by contrast, only required the creation of one single atom in a volume of space the size of a cathedral once every few hundred years. It was the same miracle, just spread out so thinly over time that it became invisible. It was a gentle rain of creation rather than a torrential flood. There is something deeply comforting about this view of reality. In the Big Bang universe, we are living in a decaying era. We are riding the debris of an explosion. We know that eventually the stars will run out of fuel, the lights will go out, and the universe will freeze in a dark heat death. The Big Bang implies a narrative of inevitable decline. We are currently in the energetic youth of the cosmos, but old age and death are guaranteed. The steady-state universe offers a reprieve from this melancholy destiny. In the steady state, the universe is a perpetual motion machine of life and light. There is no heat death. There is no end of time. There will always be new stars being born. There will always be warm worlds and flowing water. If you were to travel 1 trillion years into the future, the sky would look just as bright and beautiful as it does tonight. It is a universe of infinite optimism, where entropy is constantly battled back by the wellspring of creation. For nearly 2 decades, this theory stood toe-to-toe with the Big Bang. It drove scientific progress because it forced astronomers to go out and look for evidence. To prove Hoyle wrong, you had to find a way to show that the universe changes over time. You had to prove that the past was different from the present. This is where the dream began to crack. If the steady state was true, then the universe should look the same at all distances. When we look deep into space, we are looking back in time. If the universe is unchanging, a galaxy 10 billion light-years away should look roughly the same as a galaxy nearby. It should behave the same way. The population of stars should be similar, but in the 1950s and 60s, radio astronomers began to detect strange, powerful signals coming from the deep cosmos. These were the quasars, quasi-stellar radio sources. They were incredibly bright beacons of energy, powered by supermassive black holes feeding on gas. The critical discovery was that these quasars were only found very far away. There were none nearby. This was a devastating blow to the idea of an unchanging universe. It meant that the universe of the distant past was different from the universe of today. The past was a time of violent monsters, of active galactic nuclei blazing with the light of 1 trillion suns. The present is quieter, more sedate. The universe had evolved. It had a rowdy youth and a calmer middle age. This evolution was impossible to reconcile with the perfect cosmological principle of the steady state, which stated that the universe is the same at all times. Fred Hoyle, a fighter to the end, tried to modify his theory. He suggested that perhaps the universe had local bubbles of evolution, but the overall whole remained static. He twisted the mathematics, trying to save the elegance of his eternal model, but the final nail in the coffin arrived in 1965. 2 radio engineers, Arno Penzias and Robert Wilson, were working on a sensitive antenna in New Jersey. They were trying to calibrate it for satellite communication, but they could not get rid of a persistent, annoying background hiss. It wasn't coming from New York City. It wasn't coming from the sun. It was coming from everywhere, day and night, in every season. They had stumbled upon the cosmic microwave background radiation, the leftover heat from the Big Bang. This was the echo of the fireball. It was the smoking gun that proved the universe was once hot and dense. The steady-state theory had no way to explain this omnipresent bath of radiation. In a universe that has always been spread out and cool, there is no reason for the entire sky to glow with a uniform temperature. And so, the steady-state theory died. It was buried by data, by the cold, hard facts of radio waves and redshifts. The scientific community moved on, embracing the Big Bang as the standard model of cosmology. Fred Hoyle eventually faded from the mainstream, though he never fully conceded, arguing until his death that the Big Bang was a party girl jumping out of a cake, a flashy trick with no substance. However, even though the theory was disproven, the spirit of the steady state lingers like a ghost in the halls of modern astrophysics. We should not look back on it as a failure, but as a noble attempt to find symmetry and beauty in the dark. It challenges us to think about why we accept the idea of a beginning. It reminds us that our human intuition craves permanence. There is a specific kind of peace in reading about the steady state. It invites us to imagine a reality where we are not the debris of an accident, but participants in an eternal process. It asks us to visualize the empty spaces between the stars not as dead voids, but as fertile fields where the seeds of matter are constantly being sown. Even today, echoes of the theory survive in the most cutting-edge ideas. When cosmologists talk about dark energy, the mysterious force that is accelerating the expansion of the universe, they are describing something that behaves very much like the creation field Hoyle proposed. Dark energy is a property of space itself. As space expands, there is more dark energy. It does not dilute. In a strange irony, the universe eventually ends up dominated by this vacuum energy, looking very much like the eternal exponential expansion that Hoyle predicted, only without the new atoms popping in to keep us company. We have abandoned the steady state, but we have kept its sense of scale. We have kept the realization that the universe is vast beyond human comprehension. And deep down, there is still a part of the human psyche that rebels against the singularity. We still find it hard to accept that the clock started ticking at a specific moment. As we close the chapter on this mid-century dream, we are left with the silence of the void again. The steady state offered us a universe that breathed gently, creating matter atom by atom. It turned out to be a mirage. The real universe is noisier, messier, and more violent. It has a history. It has scars. But the desire to find a cycle, to find a rhythm that repeats, did not die with the steady state. If the universe is not a static line that goes on forever, perhaps it is a circle. If the Big Bang really happened, perhaps it was not the first one. This leads us to the next great possibility. If the universe is not a still pond, but a crashing wave, what happens when the wave pulls back? What if the expansion we see today is just half of the story? We must now turn our attention to the idea that the cosmos is alive with a great, slow respiration. We must look at the theory of the oscillating universe, where the end of everything is simply the prelude to a new beginning. In the steady state, time was a straight, infinite road. In the next theory, time is a wheel. And as we shall see, wheels can crush, but they can also carry us forward into new iterations of reality, over and over again, in a dance that never truly ends. There is a rhythm that governs our existence, a pattern so fundamental that we rarely stop to consider it. It is the rhythm of the breath. From the moment we are born until the moment we leave this world, our lives are measured in the rising and falling of our chests. We inhale, drawing the world into us. We exhale, releasing ourselves back into the world. It is a cycle of expansion and contraction, a loop of tension and release. It is the engine of life. If we look at the natural world, we see this pattern repeated everywhere. The tides of the ocean swell and recede under the pull of the moon. The seasons expand into the heat of summer and contract into the dormancy of winter. Flowers open their petals to the sun and close them against the cold of the night. It is natural, then, to ask if the universe itself follows this same ancient cadence. What if the history of the cosmos is not a straight line, but a heartbeat? What if the Big Bang was simply the sharp intake of breath, and we are currently living through the long, slow exhalation? This is the essence of the oscillating universe theory. It is a vision of reality that replaces the singular, traumatic event of a one-time creation with the majesty of an infinite cycle. It suggests that our universe is just one in a limitless series of universes, each one born from the death of the last, rising and falling like waves on an endless ocean. To visualize this, imagine standing in a vast open field and throwing a stone straight up into the air. The stone rises quickly at first, powered by the energy of your arm, but as it climbs, the invisible hand of gravity begins to pull at it. The stone slows down. It climbs higher, but each meter takes a little longer than the last. Eventually, for a single frozen microsecond, the stone hangs motionless at the peak of its arc. Then, gravity wins. The stone begins to fall, moving faster and faster until it returns to the Earth. In this analogy, the stone is the galaxies, the initial throw is the Big Bang, and gravity is the mass of the universe pulling everything back together. For decades, astronomers have tried to determine the ultimate fate of the universe by measuring this cosmic tug-of-war. We know the universe is expanding, flinging galaxies apart at tremendous speeds. But we also know that every galaxy has mass, and mass creates gravity. The Milky Way is pulling on Andromeda. The Virgo cluster is pulling on the local group. The question is there enough matter in the universe to slow the expansion down, stop it, and reverse it? If the answer is yes, then we live in a closed universe. In this scenario, the expansion we see today is temporary. It may continue for billions of years, perhaps even trillions. Civilization after civilization may rise and fall, looking up at a sky that seems to be drifting further away. But the pull of gravity is relentless. It is weak, but it has infinite reach. Over aeons, it acts like a brake on the cosmic engine. Imagine the timeline of this universe. We are currently in the phase of expansion. The galaxies are fleeing from one another. The space between them is growing. But in an oscillating universe, there will come a time far in the deep future when the expansion finally runs out of steam. The drift of the galaxies will slow to a halt. This moment, the turn of the tide, would be a time of profound stillness. If you were an astronomer living in that distant era, you would look out and see that the red shift of the galaxies has vanished. They are no longer moving away. The universe has reached its maximum size. It is a cosmic summer solstice, the longest day before the shadows begin to lengthen. And then the contraction begins. Slowly, imperceptibly at first, the galaxies start to drift toward one another. The process of the last 14 billion years reverses. The movie of the universe begins to play backward. At first, the effects would be subtle. But as the millions of years tick by, the sky begins to change. In our current expanding universe, the light from distant galaxies is stretched by the expansion of space, shifting it toward the red end of the spectrum. This is known as redshift. But in a contracting universe, the opposite happens. As the galaxies rush toward us, their light waves are compressed, squashed together like the bellows of an accordion. The light shifts toward the blue end of the spectrum. The night sky, once dark and filled with red, fading ghosts, begins to sparkle with a piercing blue intensity. As the universe shrinks, the galaxies get closer. The vast, lonely voids that currently separate the clusters of matter begin to close up. The universe becomes crowded. Galaxies that were once isolated islands begin to merge and collide with increasing frequency. The night sky becomes ablaze with the light of 1 trillion stars, all drawing nearer. It is a terrifying but strangely beautiful image. As the volume of the universe decreases, the temperature rises. The cosmic microwave background radiation, that cool, faint hiss we hear today, begins to heat up. It shifts from microwaves to infrared, then to visible light. The background of the sky itself begins to glow. At first, it is a dull red ember, like the dying coals of a fire. Then it becomes a bright orange, then a blinding white. Eventually, the universe becomes so small and so hot that the stars themselves cannot survive. They are cooked from the outside in. The planets are vaporized. The atoms are stripped of their electrons. The cosmos returns to the state it was in during the first few minutes after the Big Bang, a primordial soup of plasma and energy. This is the Big Crunch. It is the mirror image of the Big Bang. All of space, all of time, and all of matter are crushed back down into a single point. In the Standard Model, this is the end. The story stops here. But the proponents of the oscillating universe say, not so fast. They argue that the laws of physics, specifically the strange rules of quantum mechanics, might prevent the universe from crushing itself into absolute nothingness. Just as a rubber ball compresses when it hits the floor and then springs back upward, the fabric of space-time might have a limit to how much it can be squeezed. When the universe reaches this critical density, it does not die. It bounces. The implosion turns into an explosion. The Big Crunch becomes a new Big Bang. The plasma expands, cools, and forms new atoms. New stars ignite in the darkness. New galaxies swirl into shape. And perhaps on a new planet circling a new sun, new eyes look up and wonder how it all began, completely unaware that they are living in the ashes of a previous aeon. This theory, often called the Big Bounce, suggests that time is infinite. There was no beginning. There will be no end. There is only the eternal cycle of the great cosmic breath. Inhale, exhale, expansion, contraction. There is a profound philosophical comfort in this view. It aligns with the ancient wisdom of many human cultures. The Hindus speak of the kalpas, vast cycles of time, where the universe is created by Brahma, preserved by Vishnu, and destroyed by Shiva, only to be created again. The Stoics of ancient Greece believed in the eternal return, the idea that the world is destroyed by fire and reborn in exact detail over and over again. The oscillating universe brings this mythic structure into the realm of equations and gravity. It implies that we are not unique. The history of our universe is just one chapter in an endless book. It also solves the problem of what came before. Before this universe, there was the contraction of the last one. Before that, the expansion. The chain of cause and effect remains unbroken, stretching back infinitely into the past. However, like all beautiful dreams, the oscillating universe faces challenges from the cold light of data. In the mid-20th century, this theory was quite popular. But in recent decades, we have discovered something that complicates the picture: dark energy. When we look at the distant galaxies today, we do not see them slowing down as the stone thrown in the air slows down. Instead, we see them speeding up. The expansion of the universe is accelerating. It seems that there is a mysterious force pushing the galaxies apart, stronger than the gravity trying to pull them together. If dark energy is the dominant force, the universe will never contract. It will never breathe in. It will simply exhale forever, expanding until the stars burn out and the galaxies are lost in the dark. This is the scenario of the heat death, a lonely, cold ending that we will explore later. But the story of the oscillating universe is not dead. Theoretical physicists are stubborn dreamers. They suggest that perhaps dark energy is not constant. Perhaps it is a field that changes over time. Just as the seasons change, perhaps the weather of the vacuum shifts. Maybe billions of years from now, the repulsive force of dark energy will weaken and fade away. Or perhaps it will flip, transforming from a force that pushes things apart into a force that pulls them together. If that happens, the great breath will continue. The acceleration will stop. Gravity will take the reins, and the long journey back to the source will begin. There is also a problem known as entropy, the tendency of disorder to increase. In a closed system, things get messier over time. If the universe goes through cycle after cycle, some physicists argue that the entropy would build up. Each cycle would have to be longer and larger than the last. If you run that logic backward, the cycles in the past would have to be shorter and smaller. Eventually, you still hit a beginning, a first cycle that started it all. To save the eternal bounce, we have to imagine that the Big Crunch is a cleansing fire. We have to assume that when the universe is crushed down to that tiny, dense point, the slate is wiped clean. The disorder is reset. The entropy clock is wound back to zero. It is a bold assumption, but one that is necessary if we want to believe in eternity. Imagine the implications if the oscillating theory is true. It means that everything we see, the grandeur of the Milky Way, the beauty of the Orion Nebula, the structure of our own solar system, is recycled material. The atoms in your hand may have been part of a star in a universe that existed trillions of years ago. They may have been part of a different Earth, inhabited by beings who looked up at a different sky. Those beings may have wondered, just as we do, if the universe would end. They may have feared the coming darkness, and yet their end was the condition for our beginning. We are the children of their destruction, and one day, unimaginable eons from now, our universe may collapse to become the seed for what comes next. It transforms the cosmos from a linear narrative into a biological one. It makes the universe feel like a living organism, pulsing with energy. It is not a machine that was switched on and will eventually run out of battery. It is a heart that keeps beating. As we drift through these thoughts, letting the rhythm of the oscillating universe match the rhythm of our own breathing, we can feel a sense of connection to the deep time of the cosmos. We are part of the breath. We are part of the cycle. But what if the cycle is not happening in time but in space? What if the bang and the crunch are not the result of a single balloon expanding and contracting, but the result of something much larger, something happening in a dimension we cannot see? The oscillating universe assumes that 3 dimensions of space are all there is. It assumes the universe is a bubble growing and shrinking. But modern physics suggests that our bubble might just be a thin film floating in a much larger room. To understand the next possibility, we must prepare to leave the Aita world of common sense behind. We must step out of the 3 dimensions we know, left, right, forward, backward, up, down, and imagine a direction that points elsewhere. We must listen to the whispers from the higher dimension. For our next journey takes us into the realm of string theory and the brain world. Here, the Big Bang was not a beginning, and it was not a bounce. It was a collision, a cosmic car crash between two realities that drifted too close in the dark. So, let us take a final deep breath, savoring the idea of the oscillating cosmos before we let it go. We release the air from our lungs, watching it vanish into the night, and prepare to step through the veil into the bulk. We live our lives trapped in a box of 3 dimensions. We can move left or right, we can move forward or backward, and we can jump up or down. Everything we know, every object we have ever touched, and every star we have ever seen exists within this 3-dimensional stage. Our brains are hardwired to perceive the world this way. It feels complete. It feels like there is nowhere else to go. But consider for a moment a creature living on the surface of a vast, calm pond. A water strider, perhaps. To this creature, the universe is flat. It knows only the surface. It can skate north, south, east, or west. It understands the geometry of the water tension that supports it, but it has no concept of up. It has no idea that above its head there are clouds drifting in the sky or birds flying in the wind. It has no idea that below the surface there are fish swimming in the deep, cold currents. The water strider is imprisoned in 2 dimensions, completely unaware of the 3rd dimension that surrounds it on every side. For decades, physicists have wondered if we are the water striders. They have asked if our 3-dimensional universe is just a thin skin, a membrane, floating in a much larger, much vaster space that possesses 4 or 5 or even 10 dimensions. This higher dimensional space is often referred to as the bulk. This is not a flight of fancy. It is a serious mathematical proposition that arises from string theory, one of the most ambitious attempts to understand the fundamental building blocks of reality. String theory suggests that the tiny particles we see, electrons, quarks, photons, are not solid little balls, but vibrating strands of energy. And for the mathematics of these strings to work, they need room to vibrate. They need more than 3 dimensions. They need a larger orchestra pit. If this view of reality is correct, it changes the story of the Big Bang entirely. It suggests that the origin of our universe was not an explosion from a single point, but a collision between 2 worlds. Imagine 2 enormous sheets of fabric hanging on a clothesline, parallel to one another. They are blowing gently in the breeze. Most of the time they hang separate and apart, with a small gap of air between them. But every now and then, the wind shifts. The sheets billow out, they drift closer, and then, silently, they touch. In the language of modern cosmology, these sheets are called brains, short for membranes. Our entire universe, with all its galaxies and light, is trapped on one of these brains. We cannot leave it. We are stuck to it like ink on a page. We can travel anywhere within the universe, but we cannot step off the page into the bulk. But we are likely not alone. The theory suggests that there could be another brain, another universe, floating right next to ours. It could be incredibly close, perhaps only a few millimeters away across the 4th dimension. But because we cannot look in that direction, and because light cannot travel through the bulk, we cannot see it. It is a ghost world hovering just out of reach. So, where does the Big Bang fit into this picture? According to a theory known as the ekpyrotic universe, derived from the Greek word for conflagration or fire, the Big Bang was the moment those 2 brains collided. Picture these 2 vast, cold, empty membranes drifting through the higher dimensional bulk. They have existed for eons, stretching out flat and smooth. They are drawn together by a force inherent to the bulk, a gravitational attraction that pulls them across the void. The approach is slow and majestic. It is a cosmic courtship that takes billions of years. As they get closer, quantum fluctuations, ripples in the fabric of the brains, begin to interact, and then contact. The collision does not happen at a single point. It happens everywhere at once. Imagine two giant symbols crashing together. The impact releases a staggering amount of energy. The kinetic energy of the moving brains is instantly converted into heat and radiation. To an observer trapped on one of the brains, this moment would look exactly like the Big Bang. Suddenly, everywhere in the universe is filled with intense fire. The temperature skyrockets. Particles are created out of pure energy. The universe, which had been cold and empty a moment before, is now a blinding inferno of plasma. But notice the difference. There is no singularity. There is no point of infinite density where physics breaks down. The brains themselves have a finite size. They are just stretching and crashing. The temperature is high but not infinite. The density is immense but calculable. The beginning is not a magical genesis from nothing, but a physical event, a transfer of energy from the motion of the bulk into the heat of our world. This theory, pioneered by physicists like Paul Steinhardt and Neil Turok, offers a tantalizing explanation for one of the greatest mysteries of gravity. Physicists have long been puzzled by how weak gravity is compared to the other forces of nature. Think about a simple fridge magnet. That tiny piece of metal can pick up a paperclip, defying the gravitational pull of the entire planet Earth. The magnetic force of a coin-sized object defeats the gravity of a massive globe. Why is gravity so weak? String theory offers a poetic answer. Gravity is the only force that is not stuck to the brain. While light, magnetism, and nuclear forces are trapped on our sheet of paper, gravity is free to wander. It can leak off our universe and drift into the bulk. It dilutes itself, spreading out into the extra dimensions. We only feel a fraction of its true strength. This leakage suggests a profound connection to the other brain. If there is a shadow universe floating nearby, we might be able to feel its gravity. Some cosmologists have even speculated that the mysterious dark matter that holds our galaxies together might not be matter in our universe at all. It might be the gravity of stars and galaxies on the other brain, leaking across the gap, ghosting through to our side. We see the effects of their mass, but we see no light, because their light is trapped in their own dimension. If the ekpyrotic model is true, the history of the universe is a cycle much like the oscillating universe we discussed earlier, but with a different mechanism. After the collision, the two brains bounce apart. The energy of the crash drives them away from one another. As they separate, our universe cools and expands. The plasma condenses into atoms. The atoms form stars. We live our lives in this cooling phase, the aftermath of the cosmic car crash. Eventually, the energy of the expansion dissipates. The brains reach the furthest point of their separation. The universe becomes dark and empty as the stars burn out and the black holes evaporate. The brains become flat and smooth again, erasing the scars of the last cycle, and then the attraction takes over once more. The spring pulls taut. The two great membranes slow down, stop, and begin the long, slow drift back toward each other. A new cycle begins. A new Big Bang waits in the darkness of the future. This creates a vision of the cosmos that is rhythmic and eternal, but strange. It is a universe of sheets clapping together in the dark. It creates a picture of time that is infinite, punctuated by moments of creation. There is something hauntingly beautiful about this idea. It suggests that our reality is fragile. We are living on a skin, floating in a void we cannot comprehend. It makes the Big Bang feel less like an explosion and more like a thunderclap, a loud, violent event caused by the interaction of larger forces. It also changes the way we think about the void of space. We tend to think of the space between galaxies as empty, but in this model, every point in space is a window into the fourth dimension. The bulk is everywhere, just 1 millimeter away in a direction we cannot point. It is all around us, invisible and silent. This theory also addresses the fine-tuning of the universe, the fact that the laws of physics seem perfectly set up to allow life to exist. If the brains have collided trillions of times, trying out slightly different conditions each time, it is inevitable that eventually a collision would occur that produced the right temperature and the right mix of elements for us to be here. We are the winners of a cosmic lottery that has been drawn an infinite number of times. Of course, like the other theories we have explored, the brain world is difficult to prove. We cannot travel to the bulk. We cannot send a probe to the other brain. But we can look for clues. We can look for gravity waves, ripples in space-time, that might carry the signature of the collision. The Big Bang model predicts a certain pattern of gravity waves. The collision of two brains predicts a different pattern. As our detectors become more sensitive, listening to the faintest vibrations of the universe, we may one day hear the echo of that higher dimensional impact. We can also look at the high-energy experiments in particle colliders. If gravity is leaking into other dimensions, we might see energy disappear during high-speed collisions, vanishing from our known universe into the bulk. Until then, we are left with the imagery. We are left with the feeling of the water strider skating on the surface, unaware of the deep ocean beneath. It is a humbling thought. We build our maps of the universe, we draw our timelines, and we feel like we understand the shape of things. But if the string theorists are right, we are seeing only a slice of reality. We are seeing the shadow of the puppet, not the puppet itself. The whispers from the higher dimension tell us that the Big Bang was not the beginning of everything. It was just a local event. It was a loud noise in a quiet room. The true history of the cosmos lies in the movements of the bulk, in the slow, drifting dance of universes that dwarf our own. As we lie in the quiet of the night, we can imagine those great sheets drifting in the dark. We can imagine the stillness between the collisions. We can take comfort in the idea that even if our universe runs down and fades away, the mechanism for creating new worlds is always there, waiting in the dimensions we cannot see. But there is another possibility, perhaps even stranger than colliding sheets of reality. What if the universe is not floating in a bulk? What if it is hidden inside something else? What if the reason we cannot see the boundaries of our universe is that we are trapped on the inside of a celestial object that we can see in our own telescopes? We must now turn our minds to the most enigmatic objects in the cosmos, black holes. We know they are the destroyers of light and matter. We know they are the graves of dead stars. But what if they are also the cradles of new universes? What if the Big Bang was actually the formation of a black hole in a different place? What if we are living inside the event horizon of a star that collapsed billions of years ago in a universe much larger than our own? This is the black hole universe hypothesis, and to understand it, we must be willing to invert our understanding of inside and outside. We must be willing to fall into the dark. We are taught to fear the dark. In the deep primal corners of the human psyche, darkness represents the unknown, the hidden predator, and the end of the road. And in the lexicon of astronomy, there is nothing darker, nothing more final than a black hole. For decades, we have viewed black holes as the ultimate monsters of the cosmos. They are the great devourers, the cosmic drains where matter and light spiral down into oblivion, never to return. When a massive star runs out of fuel and collapses under its own weight, it punches a hole in the fabric of reality, creating a gravitational well so deep that not even light can escape its grip. In the standard narrative of the universe, a black hole is a dead end. It is a period at the end of a sentence. It is where the story stops. But nature, as we observe it here on Earth, rarely deals in dead ends. In the forest, the fallen tree becomes the soil that feeds the sapling. The death of the predator feeds the scavenger. Every ending is a seed for a new beginning. Why should the cosmos be any different? What if we have misunderstood the nature of the black hole? What if it is not a tomb, but a womb? This brings us to one of the most mind-bending and poetic hypotheses in modern cosmology, the black hole universe. This theory asks us to invert our perspective. It suggests that the singularity, that point of infinite density at the center of a black hole, is not a crushing end, but a transformative beginning. It proposes that when a black hole forms in a universe, the material that falls into it does not simply vanish or get crushed into nothingness. Instead, it reaches a critical density and bounces back, expanding outward to form a brand new universe on the other side. To the outside observer, watching from a safe distance, the black hole remains a dark, silent sphere. It looks like a heavy object sitting in space, but to an observer inside the black hole, the experience would be radically different. As the matter rebounds and expands, it would look exactly like a Big Bang. It would look like a sudden, hot expansion of space and energy, cooling down to form stars and galaxies. If this hypothesis is true, then our Big Bang was not the beginning of everything. It was simply the moment a star collapsed in a parent universe. We are living inside the event horizon of a black hole that exists in another larger reality. This idea, often referred to as cosmological natural selection, was championed by the physicist Lee Smolin. It paints a picture of reality that is not a flat sheet, but a magnificent growing fractal. It suggests a Russian nesting doll structure to existence. Imagine a grandmother universe. In this ancient cosmos, a massive star burns through its fuel and collapses. It forms a black hole. Inside that black hole, a mother universe is born. It expands, cools, and evolves. Eventually, a star in the mother universe collapses, forming a black hole, which gives birth to our universe. And now, as we look out at the black holes scattered across our own galaxy, Cygnus X1, Sagittarius A star, we are looking at the seeds of our children. Inside each of those dark spheres, a new universe might be inflating, filled with its own stars, its own planets, and perhaps its own life forms, completely cut off from us, just as we are cut off from the parent universe that created us. This theory is compelling because it solves one of the most frustrating puzzles in physics, the fine-tuning problem. Physicists have long noticed that the fundamental constants of nature, the strength of gravity, the mass of the electron, the speed of light, seem perfectly tuned to allow for the existence of stars and life. If gravity were slightly weaker, matter would never clump together to form stars. The universe would be a cold, diffuse gas. If gravity were slightly stronger, stars would burn through their fuel in a few years and die before life could evolve. If the nuclear forces were just a fraction different, carbon, the building block of life, would never form inside the hearts of stars. It feels incredibly lucky that we live in a universe with the exact right settings on the control board. It feels almost too lucky to be a coincidence. The standard Big Bang theory has no explanation for this other than blind chance. We just happened to get the winning ticket. But the black hole universe hypothesis offers a mechanism that explains this luck through evolution. Think about how biology works. Living things pass on their traits to their offspring. If a trait helps an organism survive and reproduce, that trait becomes more common. Lee Smolin argued that universes might function the same way. In this model, when a parent universe gives birth to a baby universe inside a black hole, the baby inherits the laws of physics from the parent, perhaps with tiny, random mutations, a slightly different strength of gravity, a slightly different electron mass. Now, consider which universes are fertile. A fertile universe is one that reproduces, and to reproduce, a universe needs to make black holes. To make black holes, it needs to make massive stars. So, if a universe has laws of physics that prevent stars from forming, if gravity is too weak, or the nuclear forces are wrong, that universe will be barren. It will have no black holes. It will have no children. That lineage of universes dies out. It is an evolutionary dead end. On the other hand, a universe that has the perfect conditions for star formation will produce billions of stars. Many of those stars will become black holes. Each black hole will spawn a new baby universe. Those babies will inherit the star-friendly laws of physics. They, in turn, will be fertile and produce billions more children. Over deep cosmic time, the multiverse becomes dominated by universes that are good at making stars. It becomes dominated by universes that look exactly like ours. We are not lucky. We are simply the result of billions of generations of cosmic evolution. We find ourselves in a universe rich with stars and carbon and life because only universes like this one are capable of continuing the family line. The purpose of our universe in this view is to create black holes. We, the living beings who evolve on the planets orbiting those stars, are just a happy byproduct of this reproductive process. We are the moss growing on the reproductive machinery of the cosmos. There is a strange comfort in this. It makes the universe feel less like a cold mechanical accident and more like a living system. It suggests that the laws of physics are not arbitrary, written in stone at the beginning of time, but are instead the result of a long history of adaptation and survival. But what would it actually feel like to live inside a black hole? The very idea induces claustrophobia. We imagine being crushed, trapped in a dark cell. But the mathematics of general relativity tells a different story. If you were to cross the event horizon of a sufficiently large black hole, you might not notice anything unusual at first. The event horizon is not a solid wall. It is simply a boundary in space where the escape velocity exceeds the speed of light. Once you cross it, all paths lead inward. But inward, in a black hole context, is a tricky concept. Space itself is flowing. As the new universe expands inside the horizon, space stretches. To the inhabitants, it looks infinite. The boundary, The event horizon moves away from them at the speed of light. No matter how fast they travel, they can never reach the edge to look out at the parent universe. Does this sound familiar? When we look at our own universe, we see an observable universe centered on us. There is a horizon, about 46 billion light-years away, beyond which we cannot see. Galaxies near that horizon are rushing away from us. If we tried to fly toward them, space would expand faster than we could travel. We are trapped in a bubble of causality. The geometry of our observable universe bears a suspicious resemblance to the geometry of the interior of a black hole. Some physicists have calculated the amount of matter in our universe and compared it to the size of the observable universe. They found something startling. If you take all the mass of the stars and galaxies we can see and calculate how big a black hole that mass would create, it matches the size of the observable universe almost perfectly. We fit the profile. We have the density and the radius of a black hole. This might mean that the Big Bang was not an explosion in the past, but is an ongoing event. We are still falling. We are still expanding. The collapse of the star in the parent universe is still happening, but because of the distortion of time, what takes a few seconds for the parent universe takes billions of years for us. Our 14 billion year history might be a mere blink of an eye to the entities watching the star collapse in the realm above. This perspective shifts our sense of place. We often feel small and exposed in the vast void of space. We feel like we are drifting in a fragile bubble that could pop at any moment. But if we are inside a black hole, we are protected, we are armored, we are sequestered behind a one-way membrane that nothing can penetrate. We are safe inside the shell of a gravitational giant. It also changes our view of the dark. When we look up at the night sky and see the black spaces between the stars, we are not looking at emptiness. We are looking at the structure of the womb that holds us. And when we detect the gravitational waves from black holes colliding in our own universe, ripples in space-time that wash over the Earth, we are hearing the birth cries of new universes. This theory implies that the cosmos is infinite in a way that is hard to grasp. Not infinite in width, but infinite in depth. Worlds within worlds within worlds. It is a fractal cascading downward forever. And just as we cannot communicate with the parent universe, the universes we create are lost to us. We can study the black holes. We can measure their mass and their spin. But we can never know what is happening inside them. Is there a civilization inside the black hole at the center of the Milky Way? Are they looking at their own microwave background radiation, wondering where they came from? Are they debating the Big Bang, completely unaware that their entire reality exists inside a supermassive object in our galaxy? We will never know. The event horizon is the ultimate veil of secrecy. It preserves the individuality of each universe. However, there is a somber note to this beautiful theory. Evolution is driven by reproduction, but it is also driven by death. If our universe is a living thing, subject to the pressures of selection, then it can also die. In the previous section, we discussed the heat death, the slow freezing of the cosmos. In the context of the black hole universe, the heat death is simply the aging process. As the parent black hole eventually evaporates, leaking its energy back into the parent universe through a process known as Hawking radiation, our universe might slowly dissipate. Or perhaps the connection is severed and we float free. But the cycle continues. As long as stars collapse, the chain of being remains unbroken. This hypothesis asks us to trust that the patterns of nature we see here on Earth, birth, growth, reproduction, death, are not local accidents. They are universal truths. It asks us to believe that the universe is not a static stage, nor a chaotic explosion, but a lineage, a family. It is a warm thought to hold on to as we drift towards sleep. We are not alone in the dark. We are part of a grand, growing tree of realities. We are the fruit of a seed planted in a dimension we can never visit, and we are the planters of seeds we will never see bloom. The silence before the singularity was not the silence of a void. It was the silence of a seed waiting in the soil. The Big Bang was not the beginning of the story. It was simply the moment the sprout broke the surface. But there is one final possibility we must explore. We have looked at the universe as a cycle in time. We have looked at it as a collision in higher dimensions. We have looked at it as a nesting doll of black holes. What if the answer lies in the geometry of the end itself? What if the universe does not need to crunch, or bounce, or collide? What if the very end of time, the cold, empty, motionless future, is mathematically identical to the hot, dense beginning? This is the vision of Sir Roger Penrose, a Nobel laureate who dared to suggest that the end is the beginning. In our final chapter, we will walk to the very end of the universe, past the last dying star, and watch as the concept of size itself dissolves, turning the grave of the cosmos into the cradle of a new aeon. Let us prepare to traverse the geometry of eternity. All stories, no matter how grand, eventually come to an end. This is the lesson we learn from the finite nature of our own lives, from the crumbling of ancient empires, and from the burning out of fires in the hearth. We expect the universe to follow this same rule. We have been told that the cosmos began with a bang, and we are told that it will end with a whimper. The standard forecast for the far future is a scenario known as the heat death. It is a vision of profound melancholy. As the aeons pass, the stars will exhaust their fuel and fade into darkness. The galaxies, once vibrant cities of light, will dissolve as their constituent stars are ejected into the void or swallowed by the monsters at their centers. Eventually, there will be nothing left but black holes and cold, dead remnants drifting in an ever-expanding, freezing vacuum. But even black holes are not immortal. As the physicist Stephen Hawking predicted, they slowly leak radiation. Over unimaginable timescales, years numbered with a 1 followed by 100 zeros, the black holes will evaporate. They will shrink and finally vanish in puffs of particles. When the last black hole disappears, the universe will be truly empty. There will be no matter left in the familiar sense. No atoms, no protons, no electrons, just a sea of photons, particles of light, drifting through a space that has expanded to become incomprehensibly vast. It is a state of maximum entropy, maximum disorder, and maximum cold. It seems like the final, permanent grave of reality. But in the mind of Sir Roger Penrose, a Nobel laureate and one of the most imaginative mathematical physicists of our time, this grave is actually a cradle. Penrose looked at this bleak, empty future and saw something that others had missed. He saw a geometric secret hidden in the nature of light itself. He proposed a theory called Conformal Cyclic Cosmology. It is a heavy name for a concept that is deeply elegant and surprisingly simple. It suggests that the cold, infinite end of the universe and the hot, dense beginning of the universe are, mathematically speaking, the same thing. To understand this, we must ask a strange question. What is size? How do we know how big something is? We know a meter is a meter because we have atoms to measure it against. We have the wavelength of electrons. We have the size of a proton. We have clocks that tick. Mass and time give the universe a sense of scale. They provide the ruler and the stopwatch. But in the deep future described by the heat death, there is no mass left. The universe is filled only with photons, and photons are peculiar entities. They have no mass. They travel at the speed of light, and because of the strange rules of relativity, time does not pass for a photon. From the perspective of a particle of light, the moment it is emitted and the moment it is absorbed happen instantaneously, even if billions of years have passed for us. In a universe filled only with light, there is no way to tell time. There is no way to measure distance. If you cannot measure distance, the concept of size evaporates. In this massless universe, there is no difference between being infinitely large and being infinitely small. The geometry becomes conformal, meaning that angles are preserved, but scale becomes irrelevant. Penrose argues that as the universe forgets its size, the distinction between the vast, cold future and the tiny, hot Big Bang dissolves. The infinite expansion of the old universe becomes the singularity of the new one. The end flows seamlessly into the beginning. It is a transformation that feels like magic, yet it is grounded in the rigorous geometry of space-time. Imagine a drawing by M.C. Escher where angels turn into demons, or where water flows uphill to feed the waterfall that created it. The universe performs a similar trick. It stretches so far that it snaps back to the start. In this vision, our universe is not a one-off event. It is merely one aeon in an endless chain of aeons. We are currently living in a single episode of an infinite series. Before our Big Bang, there was a previous aeon. It had its own stars, its own galaxies, and its own intelligent civilizations. That universe expanded and cooled. Its black holes evaporated, and it lost its sense of scale, triggering the transition that became our Big Bang. And one day, trillions of years from now, our own aeon will fade away, transforming into the Big Bang of the next universe. This theory implies that the singularity at the start of time was not a point of infinite density where physics broke down. It was simply the crossover point. It was the moment the old universe handed the baton to the new one. The heat of the Big Bang was not created out of nothing. It was the entropy of the previous universe being repurposed. This is a cleaner, more fluid version of the oscillating universe we discussed earlier. There is no violent crunch. The universe does not need to stop expanding and contract. It just keeps expanding forever. But the geometry of infinity wraps around to become the geometry of the infinitesimal. It breathes out, and in doing so, it breathes life into what comes next. But if this is true, if we are the sequel to a forgotten cosmos, can we find any evidence? Is the past truly lost, or are there ghosts haunting the sky? Penrose suggests that information can cross the bridge between aeons. The primary carriers of this information are gravitational waves. When massive black holes in the previous universe collided, they would have sent out distinct ripples in space-time. These ripples are so powerful that they might survive the transition. When the new aeon begins, these gravity waves from the past would leave an imprint on the new universe. They would create circular patterns in the cosmic microwave background radiation, rings of slightly different temperatures in the sky. Penrose calls these Hawking points. Astronomers have looked for these rings. Some claim to have found them, identifying concentric circles in the data from the Planck satellite that match the predictions. Others remain skeptical, arguing that the patterns could be random noise. The debate is ongoing, a polite but intense duel of statistics and simulations, but the possibility remains tantalizing. If these rings are real, they are the signatures of ghosts. We are looking at the gravitational echoes of events that happened before the Big Bang. We are seeing the crash of black holes that devoured stars in a universe that no longer exists. It would be the ultimate archaeological discovery, digging not into the soil of the earth, but into the fabric of the sky, to find the ruins of a pre-cosmic civilization. It brings a profound sense of continuity to existence. We often worry about legacy. We worry about being forgotten. We carve our names in stone. We write books. We build monuments, hoping that something of us will survive the passage of time. The heat-death scenario tells us that this is a futile hope, that eventually everything will be erased. But conformal cyclic cosmology offers a whisper of immortality. It suggests that the energy that makes up our bodies, the gravity that holds our world together, and even the disturbances we create in the fabric of space-time will play a role in shaping the universe to come. We are the architects of the next aeon. The disorder we create today becomes the raw material for the stars of tomorrow. As we reach the end of our journey through these alternative histories, we find that the silence before the singularity is not empty. It is crowded with possibilities. We started this documentary by looking at the standard model, the Big Bang, and feeling the unease of the creation from nothing. We have traveled through the steady calm of the eternal universe, the rhythmic breathing of the oscillating universe, the titanic collisions of the brain worlds, and the nesting dolls of the black hole universes. And now, we stand at the edge of Penrose's geometric eternity. What unites all these theories is a rejection of the absolute beginning. They all rebel against the idea that reality has a hard edge. They all suggest that the river of time is longer than we can see, winding back through landscapes we are only just beginning to map. Perhaps the Big Bang did happen. The evidence for the expansion and the heat is overwhelming, but the evidence that it was the first moment is non-existent. It was likely just a horizon, and just as a sailor on the ocean knows that the horizon is not the edge of the world, but simply the limit of their vision, we are learning that the singularity is not the edge of time. It is a transition, a phase change, a door. Tonight, as you lay in the dark, consider the atoms in your body. They were forged in the hearts of stars that died billions of years ago. But the energy that binds them and the space they occupy may be far older. You are made of materials that have perhaps cycled through brains, bounced through crunches, or survived the evaporation of black holes. The silence you hear is not the silence of the void. It is the hum of an engine that has been running forever. It is the quiet vibration of a string, the settling of a membrane, the geometry of an aeon turning the page. We do not need to be afraid of the vastness. We do not need to be afraid of the end. In a universe this rich, this resourceful, and this infinite, nothing is ever truly lost. The darkness is simply the canvas for the next painting. So, let the stars drift overhead. Let the galaxies rush away into the night. They are not leaving us. They are simply paving the way for the new morning that will break long after we are gone. The universe breathes. The universe flows. And we are, as we have always been, a fleeting but beautiful part of its eternal dream.